In this video, we begin our discussion of section 11.5. This is over lines and planes in space. A line, we know what a line is, straight line, and a plane being almost like a infinite piece of paper. We'll get to the planes here in a moment. So the first thing we're going to start with in this video is the equation of a line in space. So if you notice here on this three-dimensional coordinate plane, right, x, y, and z axes, I have a green line, L. And my goal is to write the equation of that line in general, given that I want the line to run in the same direction as V. Okay, so I'm going to start here. Since line L is parallel to vector V, so they are the same, and hopefully you remember this, then that means that if I take a vector from the line, right, not the line itself, but a vector from the line, then this is equal to some scalar, so t is some scalar, times the direction, right? Remember, if two vectors are parallel, they are multiples of each other, right? A linear multiple. All right, so we have that equation. We're going to use this equation and some other information. So let's pick a point, given a point, x naught, y naught, and z naught, and any other point, so we have 2 points, and any other point, and we'll call this P, and this is going to be general, x, y, z, any other point on the line. Okay, so we have a P naught and a P that is on the line. So we have some P naught, and we have some P, and that means I can actually describe that vector. So then the vector for the line, so I'll put this like weird line stuff here, that is from PO to P, so we get this notation, which is going to be the P, which is x minus the x naught for the first coordinate, y minus y naught for the second, and z minus z naught for the third. This is a vector that's on my green line. Also, let's let V, that's my directional vector, I want the line to be in that same direction. We're going to call this A, B, C, and then I'm going to put in parentheses here. This is the directional vector. All right, so let's recap. We have some line, green, and then some vector V, and we know that we want every vector on line green to be parallel to V. That's what gave us this definition here. So vector line is some constant multiple of vector V. So I picked 2 points on the green line, P naught, B sub 0, and P, just 2 different points, and then we created a vector. Hence this line right here, created a vector. And then we also I wanted some variables, some numbers with V, not variables, some parameters with V that describe V. So I have a vector for the line, and I have a vector for V. I also know from above that P naught P vector is equal to T times some vector V. That comes from the red star right there. Now I just plug things in. This is x minus x naught. This is y minus y naught. And z minus z naught. And this is equal to T is just some constant times the directional vector ABC. Now we know we can distribute that T through. It's just a constant. So we've got x minus x naught, y minus y naught, and z minus z naught equals AT, AB, sorry, not A, BT, and CT. Now, we know from the other day that when I have 2 vectors that are equal to each other, then they are equal component-wise. So I have x minus x naught equals AT. I have y minus y naught equals BT. And then z minus z naught equals CT. Now, we're trying to create an equation. And remember, x was some general, x and x naught, those were just points. I'm going to solve x because x was my general point. So I know that x is x naught plus AT. I know y is y naught plus BT. And then z is z naught plus CT. Now, notice the different variables here. What's going to happen is x naught is whatever point is given to us, and then A is the directional vector. Notice that y naught is part of the point given to us, and B is directional vector, and then Z naught and C. So if we need a line, right? Let's go for a point, for a line, sorry, for an equation of a line, we need a point, x naught, y naught, and z naught, and directional vector. And we'll call this V, and that's got to be A, B, C. All right. I have a formal definition written out on the next page, but there we go. We have that. So that's we have two ways to write this. We have the parametric equations. All right. How we write this is parametric equations. Let me write equations here. Usually these are just listed with commas. I like doing a system like that, and I just throw them in here. X equals x naught plus AT. Y equals y naught plus BT. So in the book, it's just going to list them. Z naught plus CT. Right. Notice that each equation has a T. So if I were to solve for each equation, right? So if I started solving for T, I'd have x minus x naught equals AT. And then solving for T, I have x minus x naught over A. Also, I could do this for y over y naught over B equals T. And then z minus z naught over C equals T. So since they're all equal T, we actually can set these equal to each other. So this is called symmetric equations. So we have two different types of equations for the line in 3 dimensions. One is this, and then the other one's going to be x minus x naught over A equals y minus y naught over B equals z minus z naught over C. So a couple things, we have these two forms. We are going to be given this form, and we're going to have to be able to pick up a couple things. Looking at these two forms, we're going to need to know what's the point that it goes through, and then also we need to be able to pick up the directional vectors in both of these forms. All right, so here is a formal from your book, the way they set these up. So there's a couple things I want to point out in the notes. We just talked through both of these, so I'm right here. If a directional number is 0, then the lines lie in a plane. Suppose A equals 0, so x equals x naught, line lies in the x equals x naught plane. One thing I do want to point out to this, if A is 0, right, I can't do this. That doesn't exist. So how we would write that, let's say the A equals 0, what I would write is x equals x1, and then you would have just a whole separate set of equations. Y minus y1 over B equals z minus z1 over C. So if A equals 0, then we just do x equals that number. Lines are parallel if the directional vectors are parallel. So if we want to know if two things are parallel, then we need to find the directional vectors of both lines. If they are scalar multiples of each other, right, then they are parallel. Okay, I got one equation for this video, just to kind of set us up in the right direction, give some real something to actually look at for this. So it says find the equation of the line containing both points. I'm going to find both types. So what I need, two things I need for a line. I need a point. Okay, so I have a point. The point, we're going to use the one without the fractions. 5, negative 3, negative 2. All right, and then we also need the point PQ, which is going to be negative 2/3 minus 5, 2/3 plus 3, that's minus, and then negative 2 minus 1. So PQ ends up being, right, this is negative Negative 17 thirds, 11 thirds. You can use a calculator if you need to, and then 3. I wrote this last one down the wrong way. It's gonna be there. There we go. And that's why we teach from notes. There we go. Okay, so there is my directional vector. I want to point something out, though. The whole point of the directional vector is just literally to give us a direction, to point in a direction. That doesn't mean, it doesn't even matter, like, if I were going this way, if I used that, or if I used this, or if I used that, right? Any size would give me a direction. It doesn't matter. And remember, a scalar multiple changes that. So if I want to use directional vector, and what we do is we can multiply or by anything we want to get this. So what I'm going to do is for my directional vector v, I'm going to use 3 times pq. It still has the same direction. I'm just taking the vector and making it 3 times as big. And the reason I did that is if you look at your fractions, this will get rid of everything. So v is, right, we got negative 17, 11, and 9. Don't forget to multiply your constant there if there is one. So I have a point, right, here's my point. And then I have a directional vector. So I use these two things to come up with my equation. So x equals x naught, which is negative 17, plus, I got it backwards. So here's a common mistake, and it's great that I made it. It's confusing because we have x naught plus at. My students, and even me, after time, is I will flip these without thinking. This is how I keep it straight, and most books don't even talk about this. I think the videos I usually give for extra help don't talk about it, but like all this is mx plus b, is where do you start and how does it grow? That's it. Where does it, b is y-intercept, that's the starting, and m is our slope, that's growing. So when I'm doing this, okay, the point starts at 5 and it grows by 17. So it's b plus mx. Y starts at negative 3 and the growth or the slope is 11. Z starts at negative 2 and goes up by 9. Be careful with this. This is symmetric, or not symmetric. This is parametric. Equations. And then we can also write these symmetric. How I think about these is I think right here, and all I do is solve for t in my head. Okay, so I would minus 5 and divide by negative 17. That's going to be equal to t. So I'm just going to set it equal to the next one. I add 3 and I divide by 11. So notice I'm just looking here. Add 3, divide by 11, solving for t. Then I add 2 and I divide by 9. So one thing I do want to point out, when we're pulling a point from this, it is the opposite of the inside. Like all these, the point here is, let me highlight all 3 of these. The point is 5, negative 3, negative 2. So be careful when you're pulling it from there that you're changing your signs or going backwards. Yeah, be wary of that. All right. I do want to point out one more example. There are my answers for that. I want to mention just real quick, and I'm going to write this question in. What directional vector should we use if we want our line to move along the vector 1/3, negative 3/4, and 7/2? Well, we want to make this pretty for ourselves. So what I do is I multiply, let's write this in, multiply by LCM. Least common multiple. That's the smallest number that they all go into of your denominator. We should write that. Denominator. Okay, so if we are finding our LCM of 3, 4, and 2, it's a common denominator if you want to think about that. It's 12. So I'm going to multiply this vector by 12. 1/3, negative 3/4, and 7 over 2. So the vector that we would use is 4, negative 9, 42. All pretty numbers. This can only be done, I'm going to put a star here, only can be done if we are talking direction, not distance. If we're talking distance, we can't change our vector because the length of it changes the distance covered. So if the only time I can actually change a directional vector is literally when it's a directional vector, when we're only talking about direction. If I'm talking about distance, it can't be done. I would be changing the problem.